studied so far the various methods to measure how the size of quantum fluctuations depend on the amplitude of quantum fluctuations depends on their wavelength. We averaged over boxes, and we also looked at two-point correlation functions. And we defined, therefore, the power spectrum, the fluctuations power spectrum of quantum fluctuations. But what we did so far was all static. Now, let us look at the dynamics of this. How does the dynamics of space-time affect quantum fluctuations? Remember, we assume that the system is prepared in a state 0, which is the vacuum at some early time eta naught. Later we will see why in cosmology this is a reasonable assumption. For now it's just a technical assumption, namely that the system at some early time eta naught was in a state 0, and therefore, because we are going to work in the Heisenberg picture, the system is always in the state 0. We will solve the quantum field theory with the ansatz that chi is the scale factor times phi, and that chi has this expansion in terms of mode functions and creation and annihilation operators. Our aim will be to choose the mode functions conveniently. Any such expansion is equally valid. They differ only by a change of basis in the Hilbert space. Our ambition will be to use those mode functions for which the corresponding A operators annihilate the actual state that the system is in. So technically, the challenge will be to identify, by whatever means, which vector in a Hilbert space this is. And we will use the best available criterion, which is the adiabatic vacuum criterion. And that means we will identify which mode function to use such that its A operator annihilates the physical vacuum state at early time, at the early time. And concretely, the adiabatic vacuum identification criterion is a criterion on the mode function and its time derivative. Remember, if you want to know what is the vacuum state at time eta naught, then the adiabatic vacuum identification criterion tells us the vacuum state, the adiabatic vacuum state at time eta naught, is the state annihilated by the A operator that belongs to the mode functions V, which have particular amplitudes and derivatives of amplitudes at time eta naught. So we know the initial conditions of the mode function at that time eta naught, and we know that the mode functions have to obey the Klein-Gordon equation. Therefore, this determines what the mode function is at all times, and therefore we then arrive at the solution of the quantum field theory at all times. So if we can carry this through, the benefit will be this. We will know in which state our quantum field is in, namely this one, the one annihilated by the A for the mode functions in question. And we will know explicitly the phi hat k of eta, and by Fourier transform the phi x of eta. In other words, we know all operators at all times, at all locations, and we know what state the system is in, which means we can calculate everything. All the predictions of the theory are available to us now because we have the full dynamics of all operators, and we also know the state. In particular, we can calculate the size, the amplitude of quantum fluctuations. For example, the quantum fluctuations of the amplitudes of the modes. Remember, this was the formula that we arrived at for the fluctuation spectrum in a quantum field theory on FRW spacetimes. Here, k is the co-moving momentum, and the size of the fluctuations is given by k to the power 3/2, and then you take the mode function at the time of interest. You know, the quantum fluctuations can be time dependent, the size of the quantum fluctuations can be time dependent, and it depends on the mode function, how it depends on time, and the scale factor. Really what we worked with was the square of this, and the left-hand side had two interpretations. On one hand, the left-hand side is if you square it, you get the variance in the measurement of the amplitude of the field when averaged over a box or sphere of size 1 over k, size L, which is 1 over k. Alternatively, that was the second method of making sense of that definition here. We can also view this to be the two-point function, the two-point correlator. It's the absolute value of the two-point correlator for 2 points whose distance is 1 over k. So you either interpret this as the variance of averaged amplitudes or as the amplitude of the strength of the two-point correlator. Either way, you get the same expression on the right-hand side. And now let's look at what the dependencies are on the right-hand side. Well, it depends on co-moving momentum to the power 3/2, that's one thing. But all of the time dependence is over here. Now this combination of V over A is special. Do you remember what it was, anybody? V over A? V is the mode function of the chi field. A is the scale factor. The ratio is the mode function for the phi field. So this is really the mode function for the physical field phi. But we're not calculating it directly, we calculate the V, and then we divide by A to get the mode function. So we will be interested in particular in the case where this fluctuation spectrum is increasing or somehow special. It's not decreasing as it would usually do. Normally, the smaller the length scale you look at, the smaller is the fluctuation amplitude. And we will look for deviations from that, which were caused by expansion. So all of the time dependence sits in here. And you see, we have in the denominator here the scale factor. And during an inflationary period in the universe, the scale factor is increasing in an accelerated fashion. And that means that this number here grows in an accelerated way, which would seem to indicate that the fluctuation spectrum goes down. So it would seem that as the universe expands, the fluctuations become less and less. Not going to happen. But why? Why? It's because this factor up here in the numerator can make up for that. This V, if that is suitably growing in modulus, it can make up for how this thing is growing, and so overall we might have a stable fluctuation spectrum, which would be dramatic. If this is stable over time, it would mean that the size of the quantum fluctuations of a co-moving mode stays the same over time. Do you see why that would be dramatic? It's dramatic because a co-moving mode means a different wavelength at different times, a different proper wavelength at different times. At early times, K would be corresponding to the same K corresponds to a very small wavelength, and then much later it corresponds to a very long wavelength. And if this amplitude stays stable over time, it means that even at late times, when our co-moving mode is very large wavelength, it would still fluctuate as much as it did when it was small. So the quantum fluctuations that normally are only prominent when you average over small boxes, when you look at the correlator between very nearby points, that's where you have large fluctuation spectrum. that would carry forward even to large boxes, even perhaps of cosmological size, if this amplitude is stabilized when, namely, that grows, but this grows in parallel. Let's see how or if that happens, or when that happens. So let's ask, under which circumstances does this numerator grow? Because after all, it has to make up for that. So under which circumstances does this numerator, does the mode function grow? And remember, V is the mode function for the chi field. The chi field being the ordinary mode function, the ordinary field multiplied with the scale factor. So the most efficient mechanism to enlarge that mode function occurs when the mode is non-adiabatically evolving, in the sense that the mode oscillator is inverted. We mentioned that already, right? So for the chi field, each mode obeys this harmonic oscillator equation, where this is the frequency squared. And if the frequency squared goes negative, then it corresponds to a harmonic oscillator whose potential is downwards. In such a time period, the Klein-Gordon solutions, the Klein-Gordon equation solutions are no longer oscillatory. Because if a frequency becomes imaginary, then the sine and the cosine become hyperbolic sine, hyperbolic cosine, which in fact behave exponentially. And you see how that can make up for the scale factor. If the scale factor blows up exponentially, as in the zeta universe, then we would expect that if this thing inverts, the harmonic oscillator inverts, we also get hyperbolic sine, hyperbolic cosine behavior, which is ultimately exponential, which can make up for that exponential denominator. So let's have a closer look at what is going on here inside the omega k. When can omega k squared go negative? Omega k, the frequency of the k mode in an expanding space-time for the chi field is this. There's the usual k squared term, then the mass term multiplied with the scale factor, and then here we have a double prime over a. And this is positive, that's positive, but this one can go negative. In particular, we need, and that's very important, we need that the universe is accelerating. If a double prime is larger than 0, then that is large, or it's positive anyway. So this is positive, and therefore it could be that this outweighs that and we get a negative omega squared, and the modes no longer oscillate. Instead, we would have one exponentially decaying and one exponentially increasing solution. Instead of having a sine, a cosine, instead of having a positive frequency and a negative frequency oscillation, we would have exponential increase and exponential decrease for the solutions. There's something that's often overlooked. In order for this term to be positive, the universe doesn't have to speed up. See that? See, the thing is that a double prime has to be positive, but it could be decelerating. Right? So that could also be. It could be that it's a shrinking universe that's no longer shrinking as quickly. So the shrinkage speed is decreasing, right? So you can have these effects also in those circumstances. But that's not the case we will be interested in here. We'll be interested in the case where the universe is accelerating, where the A prime is positive. Right? So A prime positive means that the universe is expanding. A double prime positive means it's not only expanding, it's expanding faster and faster. But you could also have that A prime is negative, so the universe is shrinking, but A double prime is positive, and so it's shrinking, but shrinking less and less fast. So for a harmonic oscillator that has the ordinary potential, we have a Gaussian, for example, as a solution, and the Gaussian, the ground state, would just stay where it is. It's a stable thing. But if you have the inverted harmonic oscillator potential, then let's say you start with this state and then you flip the potential, then the Gaussian will immediately start flowing apart. The particle will very quickly be very likely to be very far away because it's rolling down that potential hill. And you get these runaway solutions. There are no longer any bound states, no normalizable states anymore. All states are scattering states then. As a caveat, we should not forget the interpretation of what we are talking about. We're talking about v of x being in a harmonic oscillator here. The v of x is the mode function corresponding to the field chi. And the field chi is a blown up version of the physical field phi. Chi is a times phi. So our intuition says that when the potential of a mode flips negative, so if for some dynamical reasons over time this term starts to dominate over that term, if that happens, then the mode function will go from having a bounded modulus to having an unbounded modulus that just keeps growing very quickly. But in order to get the mode function of the physical field, we still have to divide by the scale factor. So even though that is exploding without bounds, the ratio can be finite. And it will be. And the intuition is, when the numerator and the denominator undo each other's tendencies, and so you end up with something that's approaching an asymptotic value, the picture for this is that in the Klein-Gordon equation for the phi field, for the physical phi field, there was a friction term. And it's when this friction term becomes dominant. See, when you have a harmonic oscillator that's overdamped, it no longer oscillates. And you get stuck. And that's what happens from the perspective of the original Klein-Gordon equation for the field phi. Now, the past lecture and today, so far, we looked at quantum fluctuations of fields. And we discussed just now how quantum fluctuations of fields can be dynamical. They can depend on time. Previously, we had looked at particle creation through dynamics. Let's see how the two are related. To what extent is the creation of particles in a field related to an increase in the fluctuations of a quantum field? See, both are triggered, particle creation and fluctuation amplification, are triggered by the dynamics of space-time. Let's compare. Okay, so now let's assume that at a later time, eta 1, everything was prepared as we discussed at time eta 0. Now let's look at the later time eta 1. Let's say that at the time eta 1, the evolution is adiabatic again. It may not have been adiabatic in the meantime, but let's say it is adiabatic again at time eta 1. Which is to say that for this mode, the omega k changes slowly. Okay, so if at the later time eta 1, the evolution is slow, it's adiabatic, then we can identify which vector at the time eta 1 describes the vacuum at time eta 1. In which Hilbert space vector would the system have to be at time eta 1 to be in the vacuum? Well, it's going to be the adiabatic vacuum. So we can use the adiabatic vacuum identification criterion to find out which vector in the Hilbert space it is that, if the system was in that state, would mean that the system has no particles. The adiabatic vacuum identification criterion tells us the answer in the following form. It tells us that if you want to find out what state in the Hilbert space is the vacuum now, you have to impose certain initial conditions on the mode function and its time derivative at time eta 1. And then using the Klein-Gordon equation, you get the mode function at all times, of course. In this way, you obtain a way of writing the quantum field, namely in terms of the V tilde and the A and A dagger tildes, which is such that the A tildes annihilate this vector here. Okay, so remember that overall, the adiabatic vacuum identification criterion was telling us which mode function which set of mode functions to use, such that the corresponding annihilation operators annihilate the state that's the vacuum at that point in time. Now, let's consider several cases. Case 1 is that the evolution of the mode oscillator K, and therefore of the space-time, was such that the mode oscillator changed only adiabatically, all the way from eta 0 to eta 1. What can we say then about the generating of quantum fluctuations or the generating of particles? So let's say, let's assume the evolution was adiabatic from eta 0 to eta 1. Well, what we then have is that the adiabatic vacuum identification criterion tells us at time eta 0, use the mode functions V. If we applied at the adiabatic vacuum identification criterion at time eta 1, it tells us use mode function V tilde, but because between eta 0 and eta 1 the evolution was adiabatic, the two functions are actually the same, right? Because, you know, if you apply the adiabatic vacuum identification criterion to at a time eta 0, you get a mode function there, and if you just evolve it adiabatically, you get still the same adiabatic solution. So that's a very important point. If the evolution was adiabatic, then the adiabatic vacuum identification criterion gives us the same vacuum at eta 0 and at eta 1. It tells us that this vector is the vacuum vector at time eta 0, and this same vector is describing the vacuum at time eta 1. So the two are the same, the mode functions are the same, and therefore the Bogoliubov transformation between the two is just the identity. So the state of the system, which was annihilated by the annihilation operators of the V, that state of the system is, of course, always the state of the system, but in particular, even at time eta 1, it's still the vacuum. It's not only the vacuum state at early time, it also happens to be the vacuum state at the late time eta 1. In other words, no particle creation. This is, of course, why we chose the vacuum identification criterion using the adiabatic method in the first place. If the evolution is adiabatic, there ought not be any particle creation, similar to, or in fact identical to, the observation that in a quantum harmonic oscillator, if you evolve it adiabatically, you don't excite it. Even if you change the frequency of a harmonic oscillator a lot, if you do it slowly, the fifth state will go into the fifth state, and the ground state will go into the ground state. And so similarly with the quantum field, if you change it slowly, or if you evolve the space-time underneath it slowly, so that the harmonic oscillators, so that the modes change slowly, then there should not be any particle creation. Okay, so that's not so surprising. A little comment. In that situation, the mode function V is the adiabatic solution. Remember, the adiabatic solution is simply this. See, if omega was not time dependent, then you would just have a constant here, and this would be the omega times the time interval. And the adiabatic solution is simply making this time dependent, making that time dependent. It's only true, this is only a good approximation to solving the Klein-Gordon equation if omega of k changes very slowly. If omega of k changes fast, non-adiabatically, this is not really a good solution. Try it out. I think I said it as an exercise earlier. Put the adiabatic solution into the Klein-Gordon equation and see that it doesn't obey the Klein-Gordon equation. But it almost does. There are coefficients in there in front of some offending terms, and those coefficients are negligible when omega prime and omega 2 prime, so when the frequency is not changing quickly, when omega prime is small and omega double prime is small, then this is a good solution. Now, an important observation here is that in order to predict the fluctuation spectrum, we don't need to know the phase of the mode function, we only need to know the modulus of it. Because, remember, here it is, right? We only need the modulus of the mode function to tell how large the fluctuations, what the fluctuation spectrum is. And what we see here is that in the case of adiabatic evolution, the modulus of the mode function is simply given by 1 over square root of omega k, because all of that is just a phase. Therefore, during adiabatic evolution, you can immediately tell how the fluctuation spectrum changes. It changes exactly the same way that 1 over omega of eta is changing over time. And even though the evolution may be adiabatic, it doesn't mean that the frequency cannot change at all. It can change. It just changes slowly. But this also means that the modulus of V can change. You can go from a large delta, large fluctuations, to small fluctuations, to large fluctuations in adiabatic ways. So what we see here is that even when the evolution is adiabatic, and therefore there's no particle creation, the fluctuations may still go up and down. But in this case, it's really simply because the wavelength k is changing over time. So it's not a dramatic effect. It's what we would expect anyway, because waves of different wavelengths have different size fluctuations. Now let's look at the case 2, where the evolution was not always adiabatic between eta naught and eta 1. So let's assume that the evolution was adiabatic in the neighborhood of eta naught when the system was prepared in the vacuum state. And then it's also adiabatic around eta 1, but let's say it wasn't always adiabatic in between. And this means that when you identify which is the vacuum state at time eta naught using the adiabatic vacuum identification criterion, then you get a mode function, a set of mode functions whose A will annihilate the vacuum at that time. And that set of mode functions is not the same set of mode functions that you get when you apply the vacuum identification criterion over here. So these mode functions are not exactly the same as those. They can be quite different. However, because both have to live in the same solution space of the Klein-Gordon equation, which is only 2-dimensional per k, we must have that these guys can be expressed in terms of those and vice versa. As we discussed before, there has to be a Bogoliubov transformation. So the Vk always can be expressed in terms of some coefficients ak and beta k times the V tilde and the V tilde star. Now, these are complex valued solutions, and a V and a V star are linearly independent in the complex vector space of solutions. So the two form a basis in the complex 2-dimensional solution space of the Klein-Gordon equation. The exact values of the alpha and the beta will depend on exactly what went on between eta naught and eta 1. These coefficients will depend on exactly how non-adiabatic the evolution was, and so on. in practice, you can calculate those coefficients simply by doing the following. At time eta naught, you remember what is given in all of this is the scale factor, A of eta. That's a given background evolution of the space-time. So now, at time eta naught, in order to calculate the alpha and the beta, at time eta naught, you apply the adiabatic vacuum identification criterion, which gives you initial conditions on your mode functions, solve the Klein-Gordon equation for those initial conditions, get those mode functions, right? And then do the same over here, solve the Klein-Gordon equation for the initial conditions that come from the adiabatic vacuum identification criterion. And then you have two solutions to the Klein-Gordon equation, and they must be related in such a way. So then, let us ask, what happens when you put this expression here into the formula for the fluctuation spectrum? So remember, the formula for the fluctuation spectrum was this, from the previous lecture. Here. The size of the fluctuations of the mode k at time eta is given by k to the power 3/2 and then this modulus. We will now use the squared version of that equation, where we have a k to the third and this stuff squared. So here. So I'm just carrying forward from above that equation. The fluctuation spectrum squared is given by k to the third power, and then you have 1 over a squared, and you have the v squared, right? Over there it was a v over a squared, it's a v squared over a squared, the a squared is now in front here. Okay, but now we chose to use the explicit expression for the Bogoliubov transform. We can express the mode function that occurs here, which we can use for that purpose, the mode function. In fact, we have to use for this purpose the mode function that was determined by the state in which the system really is in. That was the v corresponding to the a that annihilates the vacuum at the early time. We can simply express now that v in terms of this linear combination and plug it in here. The point of this will be the following. We want to study the relationship between particle creation on one hand and fluctuation and enhancement on the other hand. Quantum fluctuation enhancement on the other hand. And we know from the previous lecture that particle creation is proportional to beta. Okay? And now we are calculating again what the fluctuation spectrum is, and then we will see how the beta coefficients play a role in that. So we can tell how particle creation can trigger fluctuation enhancement. Okay, so the way we do it is we go into the fluctuation spectrum and then express the v mode functions as this linear combination, and then of course we get 4 terms. We get a term with the alpha squared and a term with the beta squared, and then mixed terms. Here I just plugged that into here to obtain that, and then let's work out what we get. In fact, we would get a bit of a mess. For a little bit of a simplification, we will now do the following. We will assume that the non-adiabatic period is over by eta 1. Actually, I said that already, right? We assume that the universe started out adiabatic at eta naught. It ended adiabatic at around eta 1, but in between it was not adiabatic. And by assuming that at the late time eta 2, eta 1, by assuming that at the late time eta 1, the evolution was adiabatic, we can write down what the solution is explicitly, what the solution v tilde is explicitly. It's a bit messy for the adiabatic vacuum identification criterion. In order to avoid that messiness, let's make a simplifying assumption, which is that at time eta 1, the universe not only evolved adiabatically, but didn't evolve at all. It just entered into a Minkowski phase. So you can imagine the universe, let's say, starting out in a Minkowski phase, doing some wild expansion, shrinkage, expansion, whatever, and then it ended into a Minkowski phase again, in which case we know exactly what the mode function v tilde is going to look like late, because it's the same as in Minkowski space at late times. So what we have is that in this case, when the universe ends up in a Minkowski phase, we have that the mode function v tilde is given by a plane wave and then the usual 1 over omega k. So that's going to be true for all times around eta naught and also around all times around eta 1. Now this is actually eta 1. Yeah. So what that means is that we can plug that into our formula. We have v tilde is this, and we can plug that into here, fluctuation spectrum in terms of the Bogoliubov coefficients, where the v tilde have a particular behavior, namely the usual Minkowski behavior, if the universe ends up in a Minkowski phase. So the fluctuation spectrum is given by this business, and then the 4 terms that I was talking about when you square this expression, the Bogoliubov transform, is a term proportional alpha squared, and this goes away because you have an alpha alpha star and mode function v times v star. That goes away. Similarly with the beta squared term. But then we also have a mixed term, and that gives us this phase here, which has a time dependence in it. But if we actually wanted to observe that, we would have a hard time to do so, because omega k is the frequency of the oscillation of any one of those modes. And that's generally quite fast compared to any observational period. So in practice, while this thing is oscillatory, it is very quickly oscillatory and basically washed out if we observe over any sizable amount of time. So what's left is these 2 terms. I mean, we should acknowledge that we are making an approximation here, but the bulk of what is left over is these 2 terms. And we can further simplify them. If you remember, every Bogoliubov transformation has the property that the A case and the B case obey that condition. Ultimately, that is what is left of the Vronskin condition. That's what's left from requiring that the phi pi commutation relations translate into the A dagger commutation relations. Right? You can't just take any linear combination of mode functions and have a mode function. Any linear combination of mode functions will be a solution to the Klein-Gordon equation. But it will not necessarily have the right normalization to translate the phi pi commutation relations into the A dagger commutation relations. That's the condition that enables this. Now, we know that, so we may as well use it to eliminate the A case here. So now everything is expressed in terms of the BK, of the beta K. We end up with this result, namely that the fluctuation spectrum is given by such and such prefactor. This is just the omega k squared here, the omega k here, square root of omega k. And then 1 plus 2 times beta k squared. Now, imagine there was no particle creation. Then we would have just this expression here. And this has actually the same functional behavior on k that you would expect for Minkowski space, except for that scale factor. But if we were in Minkowski space, that scale factor would be 1 anyway. And then we have here this term with the beta k. So what we see is that the deviations of the spectrum from the Minkowski behavior are proportional to 2 times beta k, which is the particle creation, the amount of particle creation that we have. So particle creation will generate quantum fluctuations. It's not fair to say, though, the other way around, because we can have an amplification of quantum fluctuations also when we don't have particle creation. And I don't mean by that the beta coefficients vanish. I mean by that there may be no concept of particle. Namely, during time periods when the potential of the harmonic oscillators is inverted, we do not have particles. The creation operators don't create particles. We don't have, the whole point of the interpretation of particles being created by the creation operator hinges on the observation that for this type of harmonic oscillator potential, we have a discrete spacing of energy levels. And whenever you raise by one energy level, you get just exactly the same amount of energy that a particle would cost that has the particular momentum k. All of that goes out of the window when the harmonic oscillator is upside down. We don't have a particle interpretation. Also, it would be interesting to couple a detector to that, right? You suggested that last time. I don't know what happens, but I've always found that an intriguing question. Okay, so how large can that get? Well, it turns out that beta k can get arbitrarily large. The Bogoliubov transformations can get arbitrarily dramatic. There is no limit to how large beta can get, the modulus of beta can get. And the reason is that it can always be made up for by a correspondingly large value of the modulus of alpha. In situations where the beta gets completely out of hand, so to speak, it goes very large and alpha goes very large, you end up with what is called squeeze states. Now, as I said already, beta, the modulus of beta is retraced back to the creation of particles in the previous lecture. We calculate what the expectation value of the number of created particles is whenever we can think of particles, and then it is just proportional to beta k squared. But this operator is not a number operator when the oscillator is upside down. So a key observation here is that the equation that we have here for the fluctuation spectrum, that equation makes sense no matter whether there is a particle interpretation or not. Even when the harmonic oscillator is upside down, we can calculate what this beta k is. So what this indicates is that the picture of quantum fields as describing fields is, in a sense, at least in this sense, more robust than the picture of quantum fields describing particles. Just because you can't always have a particle interpretation, but you can always have a field interpretation. And for example, that equation is perfectly robust under inverting the harmonic oscillator potential. Now, we studied these things in co-moving coordinates. Let us translate what we found into proper distances. And remember that they are related to each other in a time-dependent fashion. If L is the co-moving length, so it's the numerical length in a coordinate system that's actually growing with the universe, then by convention, usually the present time is chosen, the scale factor is usually, the units are usually chosen such that at the present time, A of eta now is 1, which is to say that at the present time, the co-moving coordinate system coincides with the proper length coordinate system. But that means that at a later time, the same numerical co-moving distance corresponds to a larger proper distance. I mean, for this equation to be true, you don't have to make the convention that A of eta now is 1. I'm just saying that this would be a convenient convention, that this is a convenient convention. And for the momentum, Fourier partner to this, it's just the opposite relationship with the scaling, of course. Here we have that when the co-moving momentum, the same co-moving momentum later on means a larger wavelength, but it means a larger wavelength means a smaller momentum, a smaller proper momentum. That's why the p is decreasing over time. Right? So if you hold co-moving distances fixed, later they mean larger proper distances. But if you hold the co-moving momentum fixed, later it means a smaller co-moving momentum. Because small co-moving momentum means large wavelength. Okay, so now we can translate the equation that we arrived at for the fluctuation spectrum from co-moving momenta into proper momenta. And of course, 1 over the proper momentum would give us the proper distance. So if we do this, we obtain that every occurrence of k is replaced by k over a. So a k to the third power becomes a p to the third power divided by, so k becomes a p times a, so a k to the third power becomes a p to the third power times a to the third power. So this k to the third power becomes a to the third, p to the third. This a squared is carried forward. And down here we have k squared becoming a squared p squared plus a squared m squared. That was before, that was there already before. And then let's see what we get. So here we have what? We have an a p to the third, and that a we can see if we divide. We have one a left over here, and we can also pull an a out of this square root, so they just cancel each other out, and we're just left with p to the third power over p squared plus m squared, and this expression here. And that was also the formula that we had for Minkowski space for the fluctuation spectrum. So again, we see that it was the non-adiabatic, the particle creation term, that is creating modifications to the spectrum of the fluctuations. Remember that we did our calculation under the assumption that the universe starts out in Minkowski space, does some wild things, and then ends up in Minkowski space again. And then the amount of non-adiabaticity in between is expressed in those beta coefficients. The beta coefficients measure by how much the early adiabatic solution is different from the late adiabatic solution. And what we see here too is that if the universe starts out in Minkowski space and ends up in Minkowski space, then if and only if the evolution was adiabatic in between, will we get back to exactly the same spectrum, proper spectrum, in terms of proper wavelengths or proper length. So much about the general framework. We are now getting closer to phenomenology, to doing the actual cosmology. So let's apply all of this to specific cosmological models. And we start out with the Sitter space-time. The assumption nowadays in the standard model of cosmology is that at the very beginning of the universe, very close anyway to the beginning of the universe, there was a short burst of almost exponential expansion. It will be important that it's only almost exponential, but for now, for simplicity, let's assume it is exactly exponential, just because that's mathematically much easier to deal with. So let's assume that the scale factor grew for a certain amount of time exponentially. It's just e to the power ht, where h is the Hubble constant. It's the Hubble constant during the inflationary period. Here, t is the time as read on a freely floating, co-moving observer. So if you're just drifting in the universe along with the Hubble flow, then your wristwatch time is this t. This is not the conformal time. So what we see is that the speed of the expansion is given by h. Large h, large Hubble constant, means fast exponential expansion. And a small Hubble constant means very slow, even though exponential, very slow expansion. So at the very beginning of the universe, we expect there to have been a very large h. Currently, the experimental evidence is that there is a very small h. That we have quasi-exponential expansion, accelerated expansion, but with a very small h. There is much to be said about de Sitter space that, however, is it's a very interesting space because it has high symmetries. A lot of things work the same way as in Minkowski space, but it has horizons. Please read it in your own time, the Mukhanov and Vinitsky's textbooks about de Sitter space. It's quite interesting, but we will not spend too much time on it here now because later on we will find de Sitter space is not really realistic. The actual cosmological models do not assume that the universe was really expanding exponentially. So the de Sitter horizon. The de Sitter horizon, the horizon in the de Sitter universe, in the exponentially expanding universe, will be playing an important role. And in preparation, let us look at the properties of that horizon, both for the implications of that horizon for particles and the implications of that horizon for waves. The existence of a horizon due to expansion has dramatic effects on both, on particles and on waves. So the proposition is this: objects, or any observers, who are further apart than a proper distance of 1 over h, the horizon size, can never meet, cannot communicate. Okay, so how could that be that they cannot communicate? Well, consider an observer in a galaxy A. And let us choose the origin of the co-moving coordinate system to be where this observer sits. Observer could be any one of you. Now suppose that at some time ts, this observer sends out a radio signal towards another galaxy. Another galaxy far away, not Andromeda. Andromeda is heading towards us. No, let's say you send out a radio signal to another observer at a galaxy far away, and let's assume the Milky Way goes with the Hubble flow. Let's assume the other galaxy goes with the Hubble flow. There is no peculiar velocity. They are just drifting apart because of the general expansion of the universe. So you're sending a signal now to this galaxy B, which is receding from us, from our perspective. Then what about the traveling of your radio signal? How does it travel? Well, the radio signal travels in a small amount of time delta t, the small co-moving distance delta x. And how far is that? Well, it will travel with the speed of light, which means that if you take the co-moving distance and multiply it with the scale factor, you get the proper distance, and you divide that by the time that it traveled. Well, proper distance divided by the time that it traveled has to be the speed of light, which in our units is going to be 1. So the infinitesimal version of that is to say that dx by dt is A inverse, right? Just divide this by A. So light is going to travel in a co-moving coordinate system on a trajectory where dx by dt is not 1, but is 1 over A, just because what x means changes over time. It is as if the speed was to slow down, because it gets harder and harder to cross co-moving distance, because co-moving distance means more and more distance at later times, because the coordinate system is expanding. So that differential equation is actually this differential equation. The trajectory of your beam of light is going to be dx by dt is e to the power minus ht, because that is the inverse of the scale factor. Scale factor has a plus here, and 1 over it has a minus there. So obviously we can calculate the solution to that differential equation very quickly, and here it is. This is the path of your beam of light, where c is an integration constant which is fixing where you started, where you sent off, at which location you sent off your beam of light. So let's say we choose our integration constant c in such a way that the position at the starting time, the position of the beam of light at the starting time was your position, which was x equals 0. So that means that c1, that coefficient, has to be the opposite of that. So they have to be just annihilating each other at that point. So it has to be 1 over h e to the power minus hts, because that is the same thing also, but with a minus here. So now we know what this integration coefficient is for a beam of light that you're sending off from the origin of the coordinate system. Here it is. Here's the trajectory of the radio signal that you send to the aliens in galaxy B. Now, you let that travel. Let that beam travel until it reaches galaxy B. Or does it reach galaxy B? You see, have your beam travel for an infinite amount of time, then this is the trajectory in the co-moving coordinate system. It will travel according to this trajectory. This is just a constant, the ts is here. And, well, what you see is that as t goes to plus infinity, that goes away, that term goes away, and we're just left with this. Which is to say that even if you wait an infinite amount of time, in your co-moving coordinate system, your beam of light will never travel further than this distance. Will never make it further away than that. So in other words, the beam of light will, of course, never come to a standstill. It will keep traveling. But on a co-moving map, you will see that it will never reach beyond that co-moving distance. And anybody or anything or galaxy B that's a larger co-moving distance away than that will never, ever see that light arrive, see that signal arrive. They will perhaps know, oh, that light is traveling towards me, but it's never going to reach me, because while it's doing its best, traveling at the speed of light, more space is being created between me and the beam of light because of the expansion than the light can cross at the same amount of time. So that is the horizon. That is what the horizon means. It means that two observers that are further apart at that horizon can never meet, can never communicate. Okay, and you can calculate then. Okay, so as t goes to infinity, we have this co-moving distance. So the co-moving distance can be at most that big here. And we can ask, what is the proper distance that galaxy A and galaxy B would have had at the initial time if they are at the threshold of being able to communicate with each other or not? Well, we have that the co-moving distance is this, and the proper distance, dp, is what we want to calculate. What is ds now? I think ds is dp, right? Yes, that's right. So this is the co-moving distance, and we want to know what was the proper distance. We said that if on a map 2 points, in a co-moving map, 2 points are more than, two galaxies are more than this distance apart from each other, then they will never see each other. And then, well, I'm allowing here that the starting time Ts could be any time, but for simplicity, just assume it makes no difference at all. Just assume that the starting time is 0, Ts is equal to 0, and you can tell that at Ts equal to 0, this is just the identity. So the co-moving distance is 1 over h. But at the time Ts equals 0, we also have, by convention, that the scale factor is 1, and therefore the co-moving distance is the proper distance. So the conclusion is that the maximum distance the two galaxies can be away from each other, and so that they are the borderline of being able to communicate, is 1 over h. Okay, so in a de Sitter universe, the conclusion is that if any two galaxies are further apart than 1 over h, then a light-like signal sent from one will just about reach the other, eventually at future infinity. Any closer, and they will be able to communicate. Any further away, and they cannot. So when the universe expands exponentially with a coefficient h, then 1 over h is the size of the de Sitter horizon. Okay. Yep, all of that's already said. Now, that was the particle picture. What does the expansion of space-time, and especially the acceleration and the horizon, what does that mean for waves? Now, the Klein-Gordon modes oscillate while their proper wavelengths are smaller than the horizon. We know that, of course. The proposition is that they stop oscillating and possess instead an imaginary frequency when their proper wavelength grows beyond the horizon. Right? So remember that in a de Sitter universe, the size of the horizon is a constant. It's always h. Right? So the size of the horizon is always the same. But when you look at a mode specified by a co-moving momentum k, well, the wavelength that it really means, the proper wavelength that it really stands for, depends over time. And in fact, it grows, because one co-moving mode has a larger and larger wavelength over time. And eventually, that wavelength will exceed the size of the horizon. And the proposition is that at that point, the mode oscillator will no longer be oscillating. Instead, this is exactly the regime where the harmonic oscillator goes upside down and the oscillations become exponential increase or exponential decrease. So the claim is that this discriminant here in the frequency of the harmonic oscillator can go negative exactly when the wavelength starts exceeding the size of the horizon. So let's check this. So let us first switch to conformal time. We will have to work with conformal time anyway, because our calculations have been done in conformal time. Remember, the definition of the conformal time is that it's the integral over that time. It's a reparametrization of the time axis such that this is true. And in our case here, of de Sitter, we can easily carry that out explicitly, because we know what the scale factor is. It's the exponential. 1 over the scale factor is e to the power minus ht. Then we integrate that up. We get just simply this. And that's the conformal time. By the way, just as a comment, the conformal time is also numerically equal to the conformal distance that a ray of light is traveling from the Big Bang to today. If you remember the calculation that we just did for a ray of light that travels through the universe, it gave us the same expression there. The conformal time is numerically the same as the co-moving distance that a ray of light is traveling throughout, from the beginning of the universe to today. Okay, so the important thing here is that the conformal time can be expressed in terms of the proper time of a freely floating observer in this way. And of course, C is just setting with the origin of the time axis. Notice something weird about the conformal times range is this. As t goes to minus infinity, this is a positive number that keeps growing. And therefore, this is a negative number that keeps growing. And so this goes to minus infinity. So this is all as one would intuitively expect. As time goes to minus infinity, the conformal time also goes to minus infinity. That's nice. The past is negative, and the further in the past, the further in the negative you are. But as t goes to plus infinity, towards future infinity, this thing here goes to 0. And therefore, we have that the conformal time approaches a finite value of c. And what that value is totally arbitrary. It's just an integration constant. It's just where we choose our time axis to be. But future infinity is a finite value. And the convention in the literature is to choose that integration constant, and therefore to choose the origin of our conformal time axis to be at c equals 0. This means, very important, keep that in mind for all of the intuition later on, conformal time in a de Sitter universe starts at minus infinity, that's past infinity, and then it runs up until 0. Conformal time never goes positive. Conformal time runs up to 0, eta equals 0, and that is future infinity. Okay? So conformal time runs only on a negative half axis. So all of the future is compressed into a little stretch only from some negative value to 0. So if we choose c equals 0, we end up with this relationship then between the conformal time and the proper time. Because of the a of t. Now we can solve that equation for a of t. So we can express a in terms of eta now. And you see that a of t was exponential, but in the conformal time, the scale factor behaves like 1 over eta. Okay, so the scale factor in proper time is exponential. Towards future infinity, it blows up to infinity. In conformal time, the scale factor goes like minus 1 over h eta. Why minus? How come that the scale factor can be negative? No, the scale factor is not negative. The eta is also negative, right? Remember that the conformal time is only on the negative half axis. So we have minus over a negative number, so it's really positive, 1 over h here. So what we find is that the scale factor in a de Sitter universe runs from 0. You see, if eta is very early, eta means very, very negative. This is very small here. So the scale factor is small and in the past. And then it blows up to plus infinity as eta goes to 0. Right? As eta goes to 0 from the left, this thing blows up to infinity. Just not exponentially. But that's just because we rescaled the time axis, that's all. But it's still the same de Sitter universe, of course. Now, we can make all of those formulas that we had developed earlier specific. The relationship between the chi field and the phi field is a proportionality with the scale factor here. The scale factor now is, as we just saw, minus 1 over h eta in de Sitter. So this is the exact relationship between chi and eta now. And chi obeys the Klein-Gordon equation with the omega k squared. And we can calculate exactly what the omega k squared is now for a Klein-Gordon field in de Sitter space. Remember that the omega k squared was k squared plus m squared a squared minus a double prime over a. And we know what the a is. We can just square it, easily done. And we can also calculate the second derivative of the scale factor. And what is the second derivative of the scale factor? Well, the scale factor goes like 1 over eta. So the second derivative goes like 1 over eta to the third. But we divide by a, which is going like 1 over eta. So overall, we expect something that goes like 1 over eta squared. Which is interesting because that also goes like 1 over eta squared, right? because A goes like 1 over eta. So I leave it to you as an exercise to fill in the details. The outcome is this outcome of the calculation is this. Omega squared is k squared plus m squared over h squared eta squared minus 2 over eta squared. That is all that's left from this mysterious thing. For the zeta universe, that's what it is. So now we can analyze very specifically when this is going to be negative. When the frequencies become imaginary, when the frequency squares become negative. When does that happen? Well, it happens when what we need for that is that, in particular, this expression has to be negative, right? I mean, the whole thing has to be negative for this to happen, and k squared is positive anyway. So what we need is the whole thing is positive. The whole thing we need to be negative. In particular, this must be negative. But what does that mean? What does it mean that this minus that is negative? Well, it means that this has to be smaller than that. And what that means is that we make here an assumption about the mass of the particles. Technically, we're making an assumption about the mass. If the mass was too large, see, if the mass is so large that this equality is violated, then this term is larger than that term, and you can forget about it. There's not going to be any reversal of the harmonic oscillator potentials. So memorize, large mass can screw up the fluctuation amplification through the inversion of the harmonic oscillator potential. So mass is too large, it can screw it up. But what exactly does it mean? Well, let's see. For this term to be dominant over that term, we need that m squared has to dominate over h squared, because both terms are going like 1 over eta squared. So if m squared is larger than h squared, then that term can dominate and the inversion of the potential is avoided. But we do want the inversion of the potential. So we want that this is small. M is small against h. We want that the mass is small compared to the Hubble parameter. Or, if you invert that, we want that the Compton wavelength of the particles is large compared to the Hubble horizon. And as it will turn out, in cosmology, in inflationary cosmology, this will be very well fulfilled. So, under this assumption that the Compton wavelength is larger than the Hubble horizon, this whole thing is negative, and therefore, for some k values, this whole thing is going to be negative. For large enough k values, it will still be positive. But for small enough k values, this thing goes negative. Okay? Can go negative. I mean, it depends on what you hold fixed. If you hold eta fixed, then there are k values that are, for small k values, it will be negative. For large k values, it will be positive. Or you hold the k fixed, and then it depends on the time. At early times, you might have that this is still positive, and then at late times, when eta becomes small, and therefore this whole thing becomes large, and this dominates, and it becomes negative. And that is the situation when a mode crosses the horizon. You see, if you hold k fixed, if you look at one co-moving mode, then over time it has a larger and larger wavelength. And as we will see in a moment, when that wavelength exceeds the size of the horizon, then what will happen is that the eta becomes small enough, it's late enough, such that this term dominates over that, and the whole thing goes negative. Now, to simplify things, and also because in cosmology it's justified, we will now assume that the mass is actually equal to 0. We will not only assume that this term is small compared to that, but that it's actually 0. It will go through much more smoothly if you do that. So then, then when is it that the harmonic oscillator flips its sign? So if this term is absent, when does the harmonic oscillator go from this to that? For which value of eta does the harmonic oscillator go from this to that? For which value of eta does this term dominate over that term? Well, it's when this goes through 0, right? So imagine you're looking at very early times. Eta is very, very negatively large. Then you have here a large number. It's a small number that you subtract from k squared. Therefore, frequency squared is positive. And then at later and later times, this eta term, the eta becomes smaller and smaller, denominator becomes smaller, this thing becomes larger, therefore more and more negative, and eventually it will flip the sign. It will flip the sign when this is equal to that. Okay? Therefore, it will flip the sign when eta horizon crossing, this is what's happening there, it will flip the sign when the eta obeys that it's approximately minus square root of 2 over k. You see, it's simply saying that the eta squared, k squared, is approximately 2, which is to say that this term is approximately that term. So at that time, the harmonic oscillator flips. And you can see already that for every mode, that's a different time. For every co-moving mode, its harmonic oscillator flips at a different time. Namely, as you will see, the time at which the wavelength, the proper wavelength, exceeds the size of the horizon. Okay, so our conclusion so far is this. A mode oscillates as long as eta is large compared to k. We are dropping now a factor of square root of 2. That's not going to be that important here. See, in principle, there's a factor of square root of 2 in here. So the conclusion is that a mode oscillates, the mode k oscillates, its frequency squared is a real number, as long as the eta is large compared to 1 over k. Remember, eta is negative, co-moving time, negative. So it means that for early enough time. Early enough so that the absolute value of this negative eta is larger than 1 over k. Which is also to say that the mode oscillates while eta times k is larger than 1, just multiplying through with k. And vice versa, a mode has imaginary frequency from the time onwards when the sign is reversed, when eta becomes smaller than 1 over k. Remember that late times means eta is a small negative number. As eta goes to 0 from the negative, we go towards the future infinity. So now let's re-express all of this in terms of proper wavelength. Remember that in a de Sitter universe, we have the relationship that if you multiply with a and divide by eta, you have a is equal to 1 over h, or this way, put this way, the eta is 1 over ha. And if we multiply that equation, it's just a scale factor relation, right? This is just saying the universe is expanding this fast in terms of the conformal time. If you take that equation that expresses how fast the universe is expanding and multiply it with k equal to 2 pi over L, so we multiply the left-hand side with k, and we multiply the right-hand side with 2 pi over L. See, this is a mode momentum, and this is the wavelength that it corresponds to. Then we have eta k on the left-hand side, and we have 1 over ha, 2 pi over L on the right-hand side. This product determines whether or not the harmonic oscillator is oscillating. This factor here, a times L, determines, well, that has to do with the proper length, right? This is the co-moving length, that is the proper length. So we are relating these things here. And in fact, what is h? H is the inverse of the Hubble horizon size. 1 over h is the Hubble horizon size. So in other words, on the right-hand side, we have the Hubble horizon size divided by the proper wavelength. So what we see is that whether or not this product is larger or smaller than 1, which is the criterion that decided oscillation or not oscillation, is the same question as whether the ratio of Hubble horizon size divided by proper wavelength is larger or equal to 1. So therefore, whether or not there is oscillation depends exactly on whether or not the mode, the co-moving mode, has a wavelength that is still smaller than the Hubble horizon size, which is constant in time, or whether it is has already expanded to larger than the Hubble horizon size. So here I'm just spelling it out. The A times L is the proper wavelength of a mode. And so we can write then that eta k is 2 pi over h lambda. But the h is the Hubble parameter, it's the Hubble constant, and 1 over h is the Hubble horizon. Therefore, the right-hand side is really the ratio of the two lengths. And so I think I've already said everything that on that slide. So we've just seen that the Hubble horizon means for particles that they can no longer communicate if they're further away than the Hubble horizon. It means for waves, something that's a little bit more difficult to show, but we did it. It means for waves that they stop oscillating. And yes, we only proved this for the chi field, not for the physical field phi. We really looked at the amplitudes of the chi field, but the eventual conclusion that we arrived at holds for the phi field just as well. Because the conclusion was that the chi field is oscillating, and then as soon as a mode of it has a physical wavelength that starts to exceed the Hubble horizon, it will stop oscillating. Well, the phi field differs from the chi field just by the scale factor. So therefore, if chi is not oscillating, phi is not oscillating either, because the scale factor is not oscillating. So what we will see, what we have shown here is that the phi field, the physical field, oscillates happily until it crosses the horizon, and then it actually freezes. We will see later that it actually freezes. So far, we can only say that it doesn't keep oscillating. But what we will find is that not only will it no longer oscillate, also the size of the quantum fluctuations will actually freeze. And the modulus of the mode function will become a constant. That's the same statement, right? Because the size of the modulus of the mode function gives you directly the size of the quantum fluctuations. Gives you the fluctuation spectrum. All right. Okay, so that's it for today. And in the next lecture, we will go more realistic and more realistic until we have actual models of cosmic inflation.